So I want to return to this quantum adventure we got to begin talking about last time. And in fact, for today's discussion, I'll actually focus on the project from which these photographs actually come. So it's even more closely related to this array of photos with these actual colleagues. I took that on my own phone, this photo here. We really got to use this telescope and so on. So let's jump into this second quantum adventure. And as I gave a preview of last time, this adventure is about a very specific concept from quantum theory called quantum entanglement. And as we'll see, especially in this first part for today, entanglement builds very directly on the ideas that we did focus on last time, both probabilities and superposition, and it adds, an extra additional kind of twist to that. So much like last time, the plan is to have three main kind of sections for the presentation, but with breaks in between. So after this first warm up on entanglement, I'll stop sharing screen. There'll be time for some informal questions and just discussion. Then I'll come back to part two. Part two is looking at some of the efforts to test this notion of quantum entanglement in real laboratory experiments. It's an effort that now stretches back almost exactly 50 years. We have a long baseline of efforts to conduct real world experimental tests of entanglement, many laboratories, many techniques. And I'll talk in that section about a few of the early tests, but also some of what are called loopholes in the efforts to test quantum entanglement, which we can formulate very precisely with pencil and paper. But how to really make sure we're testing that and not some other cluster of ideas, that's been its own bit of a kind of adventure for the community over the last 50 years. And then that will be the setup for this last part, where I'll talk about my own group's recent experiments in particular, as really part of this ongoing series of investigations. So again, as I think many of you, maybe all of you already know, this idea, the concept of quantum entanglement, has a very long history. It also dates back to the early years of quantum theory, going back to the 1930s, articulated by people, many of whom we were talking about last time as well, people like Albert Einstein and Erwin Schrödinger and others. Like at the end of last presentation, at the end of today's presentation, I'll have some recommendations of books that I think you and your students might especially enjoy. But I do want to highlight one in particular right away, which is a book by my colleague Louisa Gilder. It's really a marvelous book. It's been out for a number of years. You can find cheaper paperbacks online. And it's really, it's a beautiful, beautiful treatment of the long history of this concept of entanglement. And I wrote a bit about it in my own recent book, and I had shared that chapter with you today. So we've had this idea in some form or another for nearly 100 years, a long time. The articulation that we still really wrestle with, we can date to this particular article published in 1935 by Albert Einstein and two of his younger colleagues, Boris Podolsky and Nathan Rosen. And again, as many of you likely know, to this day, the paper is often referred to by the author's initials. We call this the EPR paper, Einstein, Podolsky, Rosen. This was published around the same time that Schrödinger began formulating his Schrödinger cat paradox. This is that during exactly that time when Einstein and Schrödinger were trading letters back and forth, they both having fled Berlin because of the Nazis. So what was the EPR paper all about? What got these authors so exercised, so upset actually, was that according to their theoretical analysis, taking the equations of quantum theory at face value, it looked very much to be the case that pairs of particles produced in a certain way would have this very strange behavior, where the behavior of some particle B, one member of this pair, the behavior seemed to depend on what happens to particle A, even if those two particles had moved arbitrarily far apart. And that really began to rankle Einstein. Of course, as you all know, Einstein's most significant scientific contribution was the theory of relativity, which is all about local effects, that local causes yield local effects. Nothing should be able to affect something far away arbitrarily quickly. So they went through this. This builds on the kinds of things we were looking at together last time. They considered this a quantum state of this form in this paper, which we can really see based on what we talked about last time, is a superposition like a Schrödinger cat, but of two different two-particle states. So it's not just one object that has one of two properties, the cat's alive or dead, the gunpowder's exploded or unexploded, the electron is spin up or spin down. It's now two objects whose behaviors somehow seem to be connected or entwined, or indeed entangled. So if we have two particles that we might label A and B, particle A might be measured to have spin up, and particle B would then be measured to have spin down. Or particle A might be measured to be spin down and particle B measured to be spin up, but we don't know which. We have some probabilities for either of those joint outcomes. The two particle states are now what are in superposition. And why did that upset Einstein and his colleagues so much? If we take this equation at face value, if we really follow the equations of quantum theory, there's no way to describe the behavior of particle B without already referring to the behavior of particle A. And that's what really rankled Einstein, because if they've moved really far apart, we should be able to describe particle B on its own terms. We might mess around with particle B, we might mess around with particle A, but if they're really far apart, acting on one should not affect the behavior of the other. And so in a bit more of a cartoon form, they imagine these two objects, particles A and B, that have moved arbitrarily far apart. Maybe particle A is in Princeton, New Jersey, where the authors were, and maybe particle B is in the Andromeda galaxy. They really could be very, very, very far apart. For all kinds of physics that we know and love, for Newton's laws, for Maxwell's electrodynamics, even for Einstein's relativity, it remains the case that if we do something to particle A, we interact with it, we perform a measurement on it, we hit it with a hammer, whatever we do to particle A, it takes some time for news or information or physical impact of that event here to make its way across that big intervening distance and have anything to do with particle B. And what the equations of quantum theory seem to suggest, and as the authors show in this famous paper, is that quantum theory says there should be some instantaneous synchronization, that we might hit particle A with a hammer and somehow particle B should dance instantly, not with time having elapsed in between. That's what got them so upset. Boris Podolsky, one of these authors, ran off to the New York Times before their article had even been published and said, we have this amazing critique of quantum theory. This became headline news in the paper of record in the New York Times. Einstein was supposedly so upset about this that Podolsky had run to the press before their paper had been published in the physics journal that he never spoke to Boris Podolsky again. That was one thing that upset Einstein. He remained even more upset, actually, about what he came to call the spooky action at a distance. And that phrase, again, you almost certainly have heard before. He wrote that in a private letter to his friend Max Born a dozen years later. It was in the late 1940s where Einstein still was concerned about this feature of the equations of quantum theory and how people like Max Born and Niels Bohr, and by that point, many, many other quantum physicists, didn't seem to be as disturbed by this instantaneous coordination in the way that Einstein and his colleagues had been. So 30 years later, almost exactly 30 years later, a much younger physicist named John Bell returned to this challenge or this conceptual kind of paradox that had been laid out by Einstein, Podolsky, and Rosen. In fact, as you can see from his now famous article published late in 1964, he even called his paper on the Einstein-Podolsky-Rosen paradox. It's a very elegant, very brief paper. And to boil it down, what Bell does in this article is point out that Einstein and his colleagues had really made two critical assumptions. When they concluded that there must be something wrong with quantum theory, the conclusion followed upon making certain assumptions to begin with. And Bell wanted to really clarify and make explicit the assumptions on which Einstein's argument had hinged. One of those assumptions was that each particle, particle A and particle B, has definite properties on its own before it's measured. In fact, it doesn't matter what we choose to measure, whether we measure it at all, the object has definite values for its properties. That's an assumption that Einstein and his colleagues actually had made explicit in their paper, and Bell points out how important that assumption was for their analysis. I like to think of that, again, harkening back to what we talked about last time with superposition and Schrodinger's cat. That's an assumption equivalent to saying each particle, particle A and particle B, moves through space with its own kind of logbook, that local to it, it carries its information, a complete set of information. So if we were to stop that particle on the street, so to speak, and say, right now, what's your value of spin along the x direction? It would have a value, we'd just look it up. We could equally well say, what's your spin along the y direction? It has that in its logbook as well. So that's the kind of cartoon version I at least like to think of for this first of Einstein's assumptions. And the second assumption, which again I emphasized just a moment ago, was that nothing, no information, no influence, no force, can travel across space arbitrarily quickly. And that was also totally critical for the EPR argument to follow through. their argument that in the end criticizes quantum theory. So this combination of assumptions has come to be called local realism. The local part probably makes sense. That's this information can't travel arbitrarily quickly. Local causes yield local effects. And the realism is this part, that particles have real definite properties on their own, even if we happen not to measure them. Put those together, and that pair of assumptions is often called local realism. What John Bell argued in this landmark article was that these are assumptions. They're very reasonable assumptions. They happen to hold in Newton's physics, in Maxwell's physics, even in Einstein's relativity. That doesn't prove they hold in the real world. And so Bell basically threw down the gauntlet, saying Einstein's argument rests on assumptions. Can we try to test those assumptions before we argue all night through the pipe smoke haze about who's right and how the world works? So in this same very brief article from 1964, John Bell introduced, again in kind of cartoon form or schematic form, how one might try to subject this pair of assumptions to actual experimental tests. Now we call these Bell tests in John Bell's honor. And he had an image like this. I like to joke, this is what experiments look like to people like me, who's mostly a theorist. This is very clear. There's no circuit diagrams, no soldering irons. I won't get hurt with this cartoon. So John Bell was also a theorist. His idea was to say there's some source that emits pairs of particles, and we'll talk about those in a moment. They travel off in opposite directions toward identical detectors, two identical boxes that could be very far apart, again, arbitrarily far apart in this scheme. And each box has two things that we care about. At each box, the physicist can select the question to ask. That's the detector setting. She can select what particular property to measure. If it's an electron, she might choose to measure the electron's spin along the x-axis, or its spin along the y-axis. If it's polarization for a particle of light, a photon, she could say, I'm going to measure whether the photon has horizontal or vertical polarization with respect to this angle in space. That's the question that we get to set. That's the detector setting. What specific property do you choose to measure? I'll label those with the lowercase letters A and B. So we set the question, the particle enters the box, and then this box, the detector, yields an answer. If we asked about spin along the x direction, then the answer, in this case, capital A, is either +1 or -1. If we asked about polarization, so, oh, it was horizontally polarized when I set my filter to this orientation in space, this angle. Identical setup at the distant detector. So those are the kind of bare bones ingredients for what we now call Bell tests. Again, I'll be a little more fancy, the same vocabulary as last time. We're going to consider dichotomic observables. That's a mouthful. That really just means we're going to measure things that could only have one of two possible answers, like spin. So spin is going to be either up or down. We could label those as +1 or -1. Again, it's like flipping a coin, heads or tails. You can think of it as yes, no questions. Any question we can pose that has only two possible outcomes, that Bell's formalism is especially powerful for that framework. So we'll measure properties. We'll ask questions with yes, no answers. And then we'll compare the answers from the two detectors. And since each answer, each round, can only either be a +1 or a -1, the comparison is really simple. We can compare the answers even when we had asked separate questions, because we're really just multiplying a + or -1 times a + or -1. That's what these correlation functions are. And then we'll perform, again, a statistical average over doing this many, many times. So this person might say, I'm going to measure spin along the x direction, and I get spin up. This person might say, I'm going to measure spin along, some inclined angle by some, tilted by some angle. Again, she's only going to find spin up or spin down. How do those spin measurements compare? How do the outcomes of those spin measurements compare? That's what these correlation functions are measuring for us. And then John Bell introduced this really, I think, deceptively simple looking comparison of the correlations. Again, it's very similar structure to that Leggett-Garg inequality we looked at together last time. We take a bunch of these correlations as we vary the questions being asked. We vary the detector settings between, say, one of two choices at the left-hand detector, one of two choices at the right-hand detector. How do the measurement outcomes compare as we vary the questions being asked? And we insert this deceptively simple looking, innocent looking minus sign. That turns out to matter quite a bit. What Bell then showed in this very brief article, the whole paper is only 6 pages, very, very elegant, is that if the outcome of this detector, what I'm calling capital A, the measurement outcome, like spin up, if that outcome is independent of either the question being asked at the distant detector and of the answer being given at the distant detector, either the small letter b, the detector setting at the far detector, or the measurement outcome of the far detector. If the outcome here doesn't care what happens in this box and vice versa, then this combination of correlations, this factor S, must obey an inequality. And again, it's very much like we saw the form of reasoning is very similar to that Legge-Garg inequality from last week. There's an upper bound to how strongly correlated this combination of measurements can be if we're asking questions, different questions at each device, and that the outcome here can't depend on what was done way over there, okay? You can go through this, again, your students, you can go through it together. You can just try a bunch of possibilities, just try random numbers. Every time you see a capital A in each of these correlation functions, it can either be a +1 or -1, no matter what the detector setting was. Again, think about spins. No matter how you rotate your magnets, you only either get spin up or spin down. Likewise, the capital B can only ever be a +1 or -1, no matter what orientation of your magnets you use. Just try a bunch of random +1s and -1s in this combination, and you'll find from trial and error, or you can do a little more sophisticated and do some algebra, you'll see that, that this combination of correlation functions obeys what we now call Bell's inequality, this upper bound to how strongly the outcomes can be correlated. However, again, as I'm sure you have seen before, quantum theory predicts that for some clever choices of these measurements, a certain offset angle, for example, between the direction along which we measure spin over here and the choices along which we measure spin at the distant detector, if we're clever in the questions we ask, then certain quantum systems of the sort that Einstein, Podolsky, and Rosen had identified should be more strongly correlated than what Bell's inequality would allow. That this combination S should be larger than 2. It should exceed this inequality. Okay, that's the prediction. Again, that doesn't mean that happens in the world. That's what Bell's theorem suggests, is that any local realist model, anything like here that satisfies Einstein's pair of assumptions, should obey this upper limit for this set of combinations. Quantum theory is not consistent with local realism. It predicts an observationally distinct signal. In fact, the square root of 2 is big here. It's like roughly 0.4. That's like a 40% difference. Experimentalists love that. You're not trying to find some trace answer that's off in the noise. 40% different, the peak of here compared to this supposed upper bound here. Okay, so that's still very abstract. Okay, that's still pretty, lots of moving parts, lots of math. I like to think about it this way, and this is what I wrote about in that brief chapter that I shared for today as well. Imagine there are twins, Alice and Bob, and they leave home to go study at college. And I'm required to say Alice was clearly both the more diligent and industrious of the two. That's why she comes to Cambridge, Massachusetts. She enrolls at MIT. And Bob, her perfectly affable but somewhat dim-witted brother, only gets into the University of Cambridge in the UK. They pay me to say that at MIT. So Alice comes to my Cambridge, my fair city. And soon after she arrives on campus, she goes out to a restaurant. This is non-COVID times. And the local waitstaff says, after her meal, "What would you like for dessert?" Pretty nice. He says, "Tonight you have an option. You can either have a brownie or a cookie." We can put this in the framework of a Bell test by saying he has selected the question. His detector setting is baked goods, right? He's turned the knob saying, I'm going to measure her preference along a question I care about, baked goods. And she has only one of 2 possible answers. She can either order the brownie or the cookie. Like he could measure the spin of the electron along the x-axis. It'll either be spin up or spin down. Okay, that's the way the kind of analogy works. She's delighted. She has no particular preference. She happens to order a brownie, goes home. She likes the place a lot, comes back the next night. The second time she comes, the waiter actually changes the question. He's now changed the detector setting to ask her not about baked goods, but about frozen goods. So now his question is in the A prime basis, we could say to be fancy. He's going to ask her about different kinds of desserts. She again only has one of 2 possible answers. This time he offers her either an ice cream sundae or frozen yogurt. Okay. Again, she has no decided preference. She likes them both. She happens to order one at random. She goes back over and over and over again, both for the good of science and because she loves dessert. And over the run of each of those, there's no pattern to her answers, nor is there a pattern to the order in which the waiter asks the questions. the waiter could be using some local random process, like flipping a fair coin back in the kitchen, to decide night by night which question to pose to Alice. Tonight I'll ask about baked goods because I flipped my coin and got heads. Tomorrow night I'll ask about frozen goods because I flipped the coin and got tails. And then he comes back with a series of random looking +1s and -1s each time Alice makes a choice. So if we only have access to what's in the Cambridge, Massachusetts kitchen, the log of her orders, she's asked random questions, she answers them seemingly at random as well. Unbeknownst to either Alice or her waiter, her brother Bob is now in some pub in Cambridge, England, where he's being posed similar questions at the same time. The local waiter in Cambridge, England is also flipping a coin in the kitchen. Sometimes the waiter asks Bob about baked goods, offering the same pair of options. Sometimes the waiter asks Bob about frozen goods with the same pair of options. And once again, Bob shows no particular preference. So he's ordering 50-50, whichever option he's given. And over the long haul, it just looks like a random series of +1s and -1s to a random series of questions. Then they come home for Thanksgiving. They've had almost their first full semester of college. They come back home. And what else would they talk about but what desserts they just ordered for the good of science? So they now compare their logs. And they start finding some pretty striking correlations. When they both happened to be asked about baked goods at the same moment, an ocean apart, they both gave the same answer. When they're both asked the baked goods question, they both ordered either brownies or they both ordered chocolate chip cookies. Okay. When they happened to have been asked different questions, they gave correlated answers as well. It was brownies with ice cream, not brownies with froyo, cookies with froyo. Okay, so their answers are lining up even when they're asked different questions. Again, remember we can do that comparison. It's just comparing +1s and -1s. And the really strange or surprising part was when they both happened to be asked that second question about the frozen goods. Here their answers almost always disagree. So when they both happen to be asked at the same moment about their frozen dessert preference, they tend to split, with one ordering the ice cream and the other ordering the frozen yogurt. That's what gets Einstein and his colleagues so upset. Because what seems to be happening, say in Cambridge, England, is that Bob's being posed exactly the same question and answering in a different way, in a way that seems to depend, or at least is correlated, with some activity arbitrarily far apart. It's hard to square this pattern of answers on Bob's side if Bob has some local logbook and he's answering each time based only on information that was accessible to him in his immediate surroundings. That's what Einstein thought was so spooky. That's what makes the hair stand up on the back of his head. So I'm getting close to the pausing spot. You all might have some questions soon. I just want to say that this was, again, not only pencil and paper and not only a fable about twins ordering desserts. For now nearly 50 years, physicists have tested Bell's inequality with real laboratory systems. The very first test was conducted by this gentleman, John Kaiser, who was working with a young grad student at the time named Stuart Friedman. They were at the Lawrence Berkeley Laboratory. Kaiser was a young postdoc at the time. You can see he's literally duct taping the apparatus together. The detectors were, a good sized part of a room apart. They were performing measurements on polarization entangled photons. So it wasn't spin, but it was very similar. He was preparing pairs of photons and then measuring them with the filters offset by some angle and changing the orientation. And nonetheless, he found a violation of Bell's inequality to very high statistical significance. They, I should say, Kaiser and Friedman together. 10 years later, just outside of Paris, Alain Aspect and a team there performed a kind of souped up version, and also with photons, but where they were changing the questions being asked much more rapidly. And they also found violations of Bell's inequality also by about 5 sigma. One of my favorite recent tests from just the past few years was done by a group led by this gentleman, Professor Jianwei Pan at the Chinese Academy of Sciences. They were not content with doing this in a single laboratory. What Pan did and his whole group was launch a purpose-built satellite that is even right now in low Earth orbit. It is every moment beaming down pairs of entangled photons to the surface of the Earth. And then Jianwei Pan and his group can conduct Bell tests across 1,000 kilometers or more. So I mentioned last time somewhat plaintively that for 11 months, my group's test of the neutrinos was the longest distance test of quantum mechanics because we got to 735 kilometers. 11 months later, this group published their test, a Bell test, across 1,200 kilometers. So we had a rather short-lived record. They again found very clear, statistically robust violations of Bell's inequality. So that, I think, is, to my mind, one of the most ambitious or kind of audacious experiments done recently of Bell's inequality. There's a question that almost always comes up. It's a great question. It's a question that kept John Bell himself up at night, and it turns out many others as well. If these particles are behaving with such uncanny coordination, can we use that to our advantage? Can we hook up a faster than light telegraph? Could we use this to send messages faster than light? Bell himself closes his original article in 1964 wondering if that's the case. He doesn't say yes or no, but he says that's a real question. It's not clear. That's how much the tension seemed to be with Einstein's notion of locality, right? These things seem to be coordinated at really far distances. Here's why we cannot set up a faster than light communication device using entanglement. It was first argued, at least that I know of, first time in print, as late as 1978, 14 years later, after Bell's first derivation. If we only have access to one device, if we only are sitting with Alice and her waiter in Cambridge, Massachusetts, all we see is a random string of +1s and -1s. We can be posing different questions. As we change the question, we get either a random looking +1 or -1. We only see a pattern. We only see this correlation in the data when we bring together the logbooks from those two distant detectors. Remember, in the fable, Alice and Bob had to both come home with their notebooks and then compare notes. Then they saw there was correlation in this random looking stream of +1s and -1s. That's the way it is even for these real world experiments. Only when you bring together both the list of detector settings, the list of questions asked in what order at each device, and the list of answers given, the +1s and -1s, then we see, oh my goodness, there's this amazing correlation that clearly violates Bell's inequality. We don't know that until we bring both data streams together. If we're just sitting at either Alice's restaurant or Bob's restaurant, we have literally white noise. We have a string of +1s and -1s that are so random that if we have the first 100 orders, we can't predict better than chance what the 101st will be. We have literally random noise if we only have access to one side. And that, in a nutshell, is why we can't seem to use entanglement to send messages faster than light. However, again, as some of you might know, this is still pretty important for thinking about communication. And this goes back to that Chinese Academy of Sciences satellite. They called it the Mesius satellite. That same satellite with the same entangled photons that can be used to conduct long-distance Bell tests has now been used for a long-distance quantum encrypted communication network. So that we can't use those entangled photons to send a single message faster than light, but we can use the fact that those photons share very specific shared behaviors or patterns. So if we have access to one set of the entangled photons, and our colleagues over here have access to another one, and we have a classical communication channel that is limited to the speed of light, then we can share some information safely in public about the pattern of tests we're running, and no one else would be able to eavesdrop. So then we can use that to set up a hyper-secure encryption code and use that to communicate at or below the speed of light. And so my colleague Anton Zeilinger did just that with his group based here in Austria and Zhongwei Pan's group in China, using real-time, every 1 second update quantum encryption codes based on these satellite-delivered entangled photons. That will only actually be secure. This will only be in principle secure encryption codes if quantum entanglement is real. If Einstein was simply just wrong and the world does share this strange, spooky action at a distance. So that ups the ante for the worldwide community to keep coming back and testing Bell's inequality. So I'm going to pause there and see if there are any questions on that part so far. Oh, Henry, please. Yeah.
Thank you. I was wondering, these numbers are so close to 2 root 2, I'm just trying to get a sense when experiments favor one theory over another, you get often interesting contortions, like the mechanical efforts to save the ether or the steady state theory. So I'm wondering what hidden variable theories were like on their last legs.
Yeah, Henry, thank you. It's a great question. So it turns out, and actually I'll come to this a little bit in I think the next section as well. It's a very good question. Very smart people, including John Bell himself, in fact, have been able to construct explicit constructions, real models we can write down on paper, at least real pencil and paper models, that obey all the tenets of Einstein's favored assumptions, local realism, and yet can nonetheless produce predictions that mimic those of quantum theory. But you have to start, that's where these loopholes come in. You have to start giving little kind of cheats in the experiment that you're going to analyze. And so one of those that in fact is a bit of a preview, I'll talk about it in a few minutes, is what if there was some unacknowledged coordination between the questions to be asked of each side? And if some of that information leaks to the particles, they could, in a sense, have an advance notice of the questions that will be posed to them later. So that would be perfectly, I'm now giving away the part two, that would be perfectly consistent with Einstein's assumptions, because that information would travel at or below the speed of light, everything would be local, the particles get that information, then they go on their merry way, and then they can enact this coordination while being perfectly in line with Einstein's principles. So these are the kinds of things one has to do, which makes it all the more incumbent to do these experimental tests that address these various so-called loopholes. So that's actually a bit of a preview for the kinds of things that come next. There are simpler mechanisms as well. But you're quite right that for 50 or more years, physicists have concocted various pencil and paper models that would obey local realism, but where you could tune in predictions by design. You can engineer them to mimic the predictions of quantum theory.
And people believe them?
I wouldn't call them beautiful, but they would be consistent with experimental tests, which then put up to the ante to say, well, let's design better tests, right? And as I say, for a long time, this was this was sort of the equivalent of like doing Sudoku puzzles, which is a perfectly good thing to do, right? Maybe it was a little higher, calling than that. It's about the nature of the universe, but basically it was like puzzle solving, okay? But it's in the light of that last part from right before I paused, which kind of re-excited interest in this among some members of the field. Because now it's not only a question of physics and, if you'd like, a kind of philosophy of how the world works. If the world really is consistent with an Einstein-like local realism description, then right now a multi-billion-dollar worldwide industry is a sham. That's a different kind of stake than like, I'm smart and you're wrong. Okay, those are both worthwhile pursuits, but if many private corporations, government agencies, and universities all around the world are building devices on the assumption that quantum entanglement is how the world works, then that ups the ante, because if it doesn't work that way, then, as I say, that sort of seemingly secure communication channel would in principle be hackable again. So it invests these questions with a different kind of motivation to keep trying. And that's actually what has driven some of the work in the field in the last 10 to 15 years or so. It's a great question, Henry.
Thank you.
Other questions on that? Okay, let me dive back in, and again, I'll pause in a few more minutes, but let me talk about some of these loopholes, which really does, for which Henry has already set us up very nicely. So let me jump back into that. Okay. So the standard interpretation of these now 50 years of laboratory tests is that Einstein's beloved pair of assumptions, this notion of local realism, just really is not compatible with experiment. That conclusion itself, however, rests on several assumptions, right? That's where this sort of almost kind of hyper-maniacal attention to loopholes starts to come in. The first loophole that was identified conceptually dates back to the earliest days of Bell's theorem. In fact, this was first articulated in letters, unpublished correspondence in the late 1960s between John Bell and John Clauser, who was the person I mentioned earlier, who wound up doing that very first laboratory tests together with a grad student, Stuart Friedman. So they were already writing about this in the late 1960s. It's come to be called the locality loophole. This is the easiest version, Henry, actually, of the sort of thing you have in mind. If we're not very careful in our layout through space and time of a given experiment, then we open the door for all kinds of perfectly legitimate Einstein-like explanations that could account for these strong correlations. So if we imagine a space-time diagram, so time is running up the page, and we have some, here's our laboratory floor along the x direction. If we first fixed our detector settings, if we first decide what questions to ask, I'm going to measure spin along this orientation, not that. So I fix the magnets in place. Right, if I do that first, and then I leave and get a cup of coffee, and I come back later, then I turn on my particle generator. I create the particles later, and they travel on their merry way toward the two detectors. I measure particle A first. I go for another espresso. I come back and measure particle B. You see what we've done is we've allowed for, at least in principle, the flow of all kinds of perfectly causally appropriate information within the system. There could be an information flow that could trivially account for the strong correlated outcomes, not because the world is governed by quantum theory, but because the world is governed by local realism, and we just had extra information flow we hadn't yet taken into account. And then one can write down models that would do that more formally, but that's the gist, that's a conceptual gist. Again, in terms of our story about the twins, what happens when Alice sits down? You work with teenagers all the time. Alice, by a law of nature, will whip out her phone and will take a photo and post it, right? That must happen. And so I like to think she'd use the hashtag quantum desserts. I'm not sure she'd do that. So that's like, saying, I just ordered my brownie, and texts her brother or posts to Instagram or whatever. So then Bob says, oh, Alice ordered brownie. That sounds good. I'll order one too. Okay, that's an example of this kind of information flow, which, if we're not careful with our experimental arrangement, is totally consistent with Einstein's pair of assumptions and could nonetheless account for these super strong correlated outcomes. So that was identified on pencil and paper really early, super hard to address experimentally. So even though John Clauser identified that in his correspondence before he even tried his first experiment, the electronics simply weren't in hand in 1969, 70, or 72, or anything like that. It took another 10 years, in fact. Oh, excuse me, I should say, it could also be the waiters communicating. So in the analogy, it could be Alice texting or the waiters texting, either way. So instead, what took an extra 10 years was to be able to do this in practice. First emit the particles and then determine the questions, right? So then there's no way that the particles could have known in advance what questions they would face. Okay, so they're going blind to this pop quiz. Likewise, complete the two measurements in such a way that no information from this side would be useful at that side. So neither Alice can text to Bob, nor Alice's waiter could share relevant information with his compatriot. So emit the particles, then later choose the questions, then complete each measurement. And so then even information traveling up to the speed of light is not going to be enough to account for those correlations. So as I was saying a moment ago, John Clauser recognized that he couldn't do it experimentally. It took fully 10 years until that experiment that I mentioned done in Orsay outside of Paris, led by Alain Aspect. He was able to do very fast switching of the polarizers for these entangled photons. And it was closed even more decisively in a follow-up experiment by Anton Zeilinger and his group in Austria in the late 1990s. So that's a 30-year gap between identifying this loophole on pencil and paper in around 1968-69 and actually really conclusively closing it in an experiment in the late 1990s. That just shows you the technological challenge of doing very fast switching so that the decision of what measurement to perform is made after the particles are emitted. Okay. There's a totally distinct loophole. There's a conceptually separate loophole that's often called the fair sampling or detector efficiency loophole. And this one, again, in terms of our story about the dessert orders, this is like saying, what happens if the waiter doesn't write down the wrong answer for Alice's order? He just doesn't hear her at all. He writes down no answer at all. Any real experimental device doesn't click every time a particle encounters it. It just misses some. So it's not a mistaken click. It just has zero click at all. It doesn't register an answer. So if one or both devices are missing a large fraction of the particles that come their way, if they just can't hear, like in the noisy restaurant, then the question becomes whether the measurements that are successfully completed are on a representative sample. If you're missing a bunch, it's possible that you're measuring a skewed or unrepresentative subsample of all the pairs of particles that actually come your way. So that's why it's called fair sampling. Are you sampling a small and weird unrepresentative sample of all the entangled particles that actually were shot toward the two detectors? If so, then again, it's perfectly consistent with Einstein's beloved assumptions to have a local realist model that for the subset of particles that are successfully measured would show high correlations, but would otherwise have washed out, would have been consistent with Bell's upper limit if every single pair had actually been successfully measured. And again, this was done theoretically, it was worked out as early as 1970, really early. And then people realized how large a proportion would you have to get to so that this would no longer be a legitimate explanation. You need a better than 80% efficiencies. You have to get more than 80% of each particle sent to each detector. So this no longer is an effect large enough to account for these measured correlations. So that was worked out on paper over the decades. The first experiments to really close the second loophole in real physical measurements were not completed until 2001. And that was with very slow moving ions in magnetic traps. And then the first experiments to do this with photons, with little particles of light, were really recent, actually as recently as 2013, 2 independent groups. And this was so difficult technologically that these experiments didn't even try to close the locality loophole and vice versa. So this is a different conceptual challenge that poses different experimental challenges that were so difficult that in, again, 50 years of trying, or by that point, more than 40 years of trying, people could only close the fair sampling loophole on entangled photons just a few years ago. I find that mind-boggling. The first experiment that closed both of those loopholes in a single test was done, again, remarkably recently. It was a team in Delft in the Netherlands, led by Robert Hansen, who's this gentleman here. And they published the results in Nature late in 2015. This again got headline news in the New York Times, much like the original EPR paper. This time it was not celebrating Einstein's win. Sorry, Einstein, this rather snarky headline says. Quantum study suggests spooky action is real. This is a tour de force experiment, it's really quite beautiful. The first one to close both loopholes 1 and 2 in 2015 when Bell's inequality was published in 1964, okay? Very soon on the heels of this test, 2 other groups using different experimental techniques and even different kinds of particles also managed to close loopholes 1 and 2 in their own same experiment. So by the end, literally by December 2015, we had 3 groups that had successfully done this, those two loopholes. There's a third loophole. This is one I began to explain actually to Henry just a few moments ago. And again, I'll pause soon, but this is the third one that again has actually a long history in the literature, but was only getting more attention either theoretically or experimentally in the last few years. This one is often called the freedom of choice loophole. And that's a question about whether the particle's properties, the particles are emitted from this source, had any correlation with the detector settings, with the questions about to be asked of them, okay? And so it's not about saying, did Alice tweet to her brother, or did this waiter contact that waiter? It's not about direct communication during a given experimental run. It's actually asking about their shared causal past. So I mentioned in the fable, in the story, that both waiters are deciding based on some local random process, like flipping a coin in the kitchen, which question I ask run by run. So Alice's waiter will say, I flipped a coin, tonight I'll ask her about baked goods. I flipped a coin, tonight I'll ask her about frozen goods, and Bob's waiter in Cambridge, England is doing the same thing. That happens in the past. What if something that we hadn't taken into account had either nudged the coins, maybe they're not fair coins after all, or had gotten a preview of what that outcome is going to be, and then could communicate that information to the source of particles before the particles left the station. This is still information flowing in principle at or below the speed of light. It's therefore perfectly consistent with Einstein's postulates. And the idea now is that the twins, Alice and Bob, before they go to college, have a complete list of the questions they'll ask in order. Or in fact, you don't even need a complete list. You just need a little bit, you need to be able to guess better than chance what questions they'll be asked time 1, time 2, time 3, and so on. Then they can coordinate their local logbooks and carry the logbooks with them as they head off to the different Cambridges. It turns out an incredibly small amount of coordination of this sort, of the prior sort, is enough to mimic all the predictions of quantum mechanics. And again, that comes back to Henry's question. So my colleagues and I actually wrote down explicit models of this form. They're ugly. I'm not going to say these are beautiful constructions. But the point is that it's a proof of principle, that being perfectly consistent with Einstein's local realist assumptions, if you allow for a very tiny statistical correlation between the selection of questions and the properties of these particles through a mechanism like this, through their shared causal past, let's say, then you can mimic all the predictions of quantum mechanics. This loophole, it turns out you can make these models more than 20 times more efficient than the models of that first kind, the locality loophole. In the locality loophole, Alice has to send 1 bit of information, at least 1 bit at or below the speed of light, to Bob, or the waiter to the other waiter, which could be something like spin up. You can make that as +1. She has to text +1. Or she just has to text, he asked about baked goods, A instead of B. 1 bit. For this kind of mechanism, or we might say conspiracy, to mimic all the strong correlations of quantum theory, the statistical correlations have to be 1/20th of 1 bit. In fact, 1/22nd of 1 bit. 20 times less mutual information is the technical term. Enough statistical correlation among these moving parts for this kind of conspiracy from the past to enable a local realist model to mimic all the predictions of quantum theory while remaining true to Einstein's assumptions. I think that's pretty astonishing. So this took us a while to work out, but that's a more recent analysis, theoretical analysis. So now it comes back to experiments with these $1 billion and these fancy satellites and this secret communication channels. If we're not simply going to assume that the particle's properties are independent of the detector setting sort of by fiat, if we really want to test that, how do we test that experimentally? How might we subject this third loophole of freedom of choice to experimental test? There was one I think, again, very fun and clever way that some colleagues did. I was not involved with this, but several of my colleagues were. They called themselves the Big Bell Test Collaboration. It was 100+ physicists in all. You can see the stats here. They were distributed across 12 laboratories in 11 countries on 5 continents. So that's a lot of physicists. Plus, they recruited 100,000 citizen volunteers. This is a citizen science project. They recruited them in advance so that on one single day in November 2016, these 100,000 volunteers would have downloaded a specially built game on their phones or tablets that would use fancy machine learning techniques to guess their own play at some handheld video game device. Your goal is to produce numbers so random that the machine learning algorithm can't guess your next number. So you want to basically produce +1, -1, +1 in a way that's so random, even this fancy algorithm can't guess your next one better than chance. Meanwhile, and you get more points if you outsmart it, so you have an incentive that's the gamification. Meanwhile, through this real-time network, it's piping through all these quasi-random +1s and -1s from 100,000 volunteers, scrambling in random orders, sending to 12 labs on 5 continents, and those are the inputs for measuring spin along this direction or that direction in 12 experiments done throughout the course of 1 day in November of 2016. And every single lab, using their sources of randomness through this way, found clear violations of Bell's inequality. So again, I'll pause there. That again shows, I think, a bit playfully, some of the lengths to which some of these groups want to go to test this third loophole. And then for last one, I'll talk about what my own group did, which was, we did not rely on the kindness of strangers. We had a different approach. So Joseph, please go ahead.
So I don't know if this question will make sense, but it seems to me like part of the reason that people are going to these extremes to test these loopholes is because we, as humans, we just don't have intuition naturally about quantum theory. Because in my head, it's you could do some of these same type of tests for some other experiments that we would never do because oh, it matches our intuition. Who cares, right? So I guess the question is do you think it's ever possible to get intuition about quantum theory, or do you think it makes sense to be thinking that we even need that intuition about quantum theory, or should we just be sort of a little bit more accepting that we don't have it?
Joseph, thank you. That's a great question. It harkens back, I think, to a question that Peter had asked last time too, or at least seems similar to me when he was asking for help for when his own students ask about electrons in an atom. So what I think the upshot of 50 years of testing Bell's inequality, let's take it just for entanglement. What I think the upshot is that we've ruled out a bunch of things that can't account for these spooky correlations. So we can make all kinds of models that would be of the sort that we might either find intuitive or at least consistent with how we think about Newton's laws and Maxwell's laws and Einstein's relativity. And we just shot them all down one at a time. So we say, why are these outcomes correlated? Well, not because of this, and not because of that, and not because of that, which is very different from saying because of this. I still don't have a picture, a kind of narrative or cartoon in my head where I could say A followed B and I could trace it through space and time in the way that I can if I'm following, a baseball with Newton's laws, or even, the behavior of a classical magnet due to Maxwell's equations. I take your point, Jozo. I think you're right that what we don't have as a community is a clear intuition that would give us of the same kind that we seem to have developed for many other parts of physics and chemistry and biology and other areas, sociology for that matter. What we don't seem to have in many of these instances is a visualizable kind of mechanistic A led to B, this gear meshed with that, gear, and that wheel turned, and these kinds of things that we can devise for many, many other consequential physical systems. And it's not for lack of trying. I think we can get intuition in certain things a lot, as we talked about last time. A lot of these things come down to the play of waves. We have a lot of intuitions about waves. It's just sometimes we push those too far and actually the analogy breaks. So we can get intuitions in a bounded sense. And maybe that's where we are. But we don't have the kind of story from start to finish in a visualizable, mechanical, A knocked into B kind of narrative that we usually can really put together, even for black holes, even for very exotic relativistic phenomena. We can often put together that kind of cartoon, these things unfolded in space and time. So I don't think it's hopeless. I think the equations do often give us seemingly unambiguous things to go out and ask about and test, right? And then we have to be careful with our tests to make sure we're not letting open the kind of the back door. But it's still not the same thing as saying, I close my eyes, I picture this thing knocking into that thing. It's not billiard balls, it's not, And so it's a series of saying it's not this, not that, or it's sort of like this except for that, right? And that can be, it's hard for me, it's hard for, I'm sure it's hard for high school students and for high school teachers, hard for all of us. So that's how I tend to think about it, is it's a bunch of partial, like broken analogies, and we get a patchwork, and we do the best we can that way, I think. Ben, please go ahead.
Hey, David, thanks for taking my question. I kind of wanted to build off this. I was thinking, and I liked what you were saying about the idea of models being sort of, there's always a limit to what a model can do. If it wasn't a model, then it'd be reality.
Right.
My question hooks into, did this maybe hook into the idea of that wave particle duality? I know that's one of the things my students often get hooked on, and I find difficult, could it be hooked into that we want to say, well, is it a wave or is it a particle? And then we have to say, like, well, it's sometimes this and sometimes that, and it just sort of depends on how you look at it.
I think that's a perfect example of this. I think that's exactly right. So we have lots of, I think each of us have, and our students have lots of intuitions about particles, again, billiard balls, scattering, or whatever it might be. Separately, we have lots of intuitions about waves, interference and superposition, all these things, even if we don't use those words, polarization. And the problem is that they won't both apply all the time in the quantum realm. They'll both apply each part of the time. And Niels Bohr thought that was a very deep insight. He thought that was the big philosophical lesson, is that we need both and can't use them. We need two mutually exclusive sets of ideas that we can't use at once, but we need them both. And that's, again, different from kind of gears meshing or other parts of physics. And so wave particle duality, I think, is a great one to, let's say, hone our intuition, because we learn a lot from thinking about waves, and we learn a lot separately about thinking about particles. And the trickiness is that they don't mesh, and we can't use them both together. So we have to be really kind of contextual. And this is going to get us this far in this part of our thinking about this experiment, or whatever the case may be. Yeah. Let me jump into the last part, because now I want to get to my own group's experiment, because it's, frankly, I thought really fun. Barry, go ahead, and then I'll go move on.
So Professor, my question is, the explanation you provide for the Bell correlation is that when Alice and Bob make their measurement, they split in two branches. From the point of view of Alice, there are multiple copies of Bob, and from the point of view of Bob, there are multiple copies of Alice. So that leads us to kind of think that the many world views, is it connected to many world views, or Maybe it contradicts.
I don't think it contradicts it, but what the many world view on its own won't get us to, I think, is why each branch of split Alice sees these remarkable correlations with her version of Bob in her split path. So why is it still mutual consistent within each branch of that tree that they're measuring these very strong correlations? So the many worlds is one effort, at least, to address the so-called measurement problem. Why does she get spin up and not spin down if the particle was in superposition ahead of time? It was designed to try to address that. But I don't think many worlds on its own will tell us why in these two particle superposition states, each of her self-consistent branches sees this very particular pattern, and each of Bob's does as well. It doesn't mean it contradicts it, but I'm not sure that gives us the answer either. It's just, I think the problem gets carried over as something that many worlds would also have to contend with, as would any of the other approaches to the measurement problem.
Thank you. Thank
Yeah,
you.
it's a good question. Okay, let me turn to that last part, and we'll have time for some more discussion at the very end as well. So I told you about the Big Bell test and their crazy thing with human volunteers. What my colleagues and I decided to do was turn the universe itself into a pair of random number generators. So not ask for teenagers to play video games, which they're going to do anyway, but actually try to set these detector settings, these questions to ask of the pairs of particles, using events that themselves should have been as uncorrelated as physically possible. And so my colleagues and I are coming to this from astrophysics and cosmology. We're used to thinking about the universe as really, really big scales. So we wanted to know, could the universe help us out? So we wanted to, in particular, we wanted to perform real-time astronomical measurements of some property of light from that corner of the sky, and at the same time, some property of light at the other detector from the opposite side of the sky, and measure those properties really, really quickly, not to measure entanglement between them. We want those, the light from the sky, to be as unentangled with each other as possible. So we have two separated, uncorrelated random strings of numbers, and we use those as inputs on our earthbound test here. And I'll say more about that in the coming slides. But that's the idea behind these cosmic Bell tests. So now I'm going to go into my Carl Sagan mode and talk about billions and billions. As you know, the universe is billions of years old. It's about 14 billion years since the Big Bang. And it's also tens of billions of light years across. We get light from objects that are very, very, very far away. So it's really convenient to actually take that huge vastness of the universe and its rate of stretching, its expansion, take that into account and kind of scale it out. So cosmologists, astrophysicists do this all the time. We use special coordinates which take into account the uniform universal stretching of space. The universe is bigger now than it was last week, bigger than it was 3 years ago, etc. But it's getting bigger the same way in each location, so it's shared. Let's kind of scale it out. So the physical distance we measure with meter sticks or kilometers I'll call x, the physical distance. This little r is called the co-moving distance, which is the distance that's left over when you take out the uniform universal stretching of space. This a of t is called the scale factor that says at any moment, what's the average distance between two objects and how has it changed since the last time you checked? That's the universal scaling. So co-moving distance, and likewise, we're going to use a variable clock rate. This was a little more abstract. This was called conformal time. We change the rate at which we consider our clock to have ticked based on the changing rate of expansion of the universe. That's very abstract. I promise you, we do this all the time when we use things like a Mercator projection of the Earth. This is also a conformal mapping. This is a space-space conformal map, latitude and longitude. We're going to do the same thing, but for a space-time map. And so this introduces some well understood distortions. It looks like, Antarctica is going to swallow the rest of us. It's not. That's one of these space-dependent, location-dependent distortions from this variable, the equivalent of this variable clock rate. On the other hand, it introduces some really great simplifications. Why do we bother with this in astrophysics? Because it makes light rays travel on 45-degree diagonals again, just like they would in special relativity. So if we plot space and time in these convenient coordinates, conformal time, this variable clock rate, running up the vertical axis, and co-moving time, taking into account that universal stretching along horizontal, then we just sit still. Here we are. And light from different parts of the sky comes to us, and the light can only travel on 45-degree diagonals, just like it would if we were doing special relativity again. And we're using, setting the speed of light to 1. Okay, so that's a little counterintuitive, but it's really like what we do all the time, and it buys us a lot, because now we can map the entire history of the universe, which in a little self-centered way leads just to my experiment. Okay, I've drawn a map from the Big Bang to me. Okay, that's a little much. But this is where we can map all the relevant events in this experiment. Okay, not in all of our lives, but in this experiment, the Big Bang happens. That's our t equals 0. This is like the South Pole. Okay, now one pointed and stretched into a line, just like the South Pole on a Mercator projection. A little while later, so time has gone by, a little while later, some blob of matter lights up and starts emitting light. That's a very early galaxy. It's a distant quasar. The light from that galaxy can only travel in these maps along 45 degrees. So it starts its journey toward where we're sitting in the middle. It's starting to travel toward the Earth over cosmic history. This could now be more than 10 billion years. Okay. Meanwhile, on the other side of the sky, a little after the Big Bang, some other clump of matter, as distant from this one as practically as it could be, condenses into an early galaxy, starts to light up. Its light starts traveling toward the Earth. So now it's moving along some other 45-degree diagonal. Okay. While that light is on its way, we now sit here in the middle on Earth, and we turn on our laser and emit entangled particles. And I'll say more about that part in a moment. But here we are on Earth starting our experiment before those light beams from those distant quasars have even reached the Earth yet, right? See, here at this time, I've turned on my particle producer, my laser, and the crystal and all that. And after the particles are in flight, I first measure properties of that cosmic light, and that locally determines the questions to be asked when later on still, the entangled particles reach their detectors. Okay, that's the space-time structure that's going on. Now, just like in that conspiracy I showed you before, that third freedom of choice kind of mechanism, it's quite possible, it's consistent with Einstein's relativity at least, to say that some event within what we call the past light cone of, say, this quasar emission event could have either affected the light that got emitted, it could have made it like an unfair coin, it could have nudged the coin, or could have acted on information available to it and given a preview to Earth of what this light is going to be like when it arrives. It can either nudge the coin and let us know, or it could simply observe properties of the coin and tell us, oh, here's what it's going to be. So this cosmic bell protocol doesn't eliminate this third loophole, it very tightly constrains it. It pushes it back and says, if we're going to try to account for the results of our experiment in an Einstein-like way, then the Einstein-like mechanism had to be set in motion no more recently than the more recent of the two quasar emissions. It sets a time limit for a non-quantum theory explanation. It doesn't rule it out, but it constrains it to very early in cosmic history, very far away from the Earth. That was our approach for trying to address this third loophole. So that's the causal structure of space-time using these fun, fancy coordinates. The last thing you have to worry about if you're going to do this experiment, that you have to get the causality right, is sometime after the quasars emit their light and before you turn on your laser, you have to get money. It always comes down to when you're going to get your grant money. If you get your grant money here, it's not going to work. Okay, so you after quasar, pre-laser, get your grant. That was actually the hardest part of the whole experiment. Okay, we did get the grant. We put together this international team, grew to be about 20 members. This was Andy Friedman, at the time a postdoc working with me, and his good friend Jason Galicchio. They were both quite young physicists at the time. The three of us had proposed this new kind of experiment, and we were overjoyed when we pitched it to Anton Zeilinger, who's been doing these experimental tests for decades. And he was tickled, and together we built a group with he and many of his really quite remarkable younger colleagues as well. And then we brought my friend and mentor, Alan Guth in. Alan is an expert in things like the Big Bang and cosmology. He and I run a group together at MIT. So we had a number of senior physicists, a large number of really quite amazing younger physicists, with support from the National Science Foundation and the Austrian Academy of Sciences, split over 9 hours of time zones just to get the group to work. Okay, so that's what brought me to the top of this mountain that I keep flashing at the start of these slides. The Roque de los Muchachos Observatory at the top of the La Palma Island in the Canary Islands off the coast of Morocco. Really is just gorgeous. You can see you're typically above the cloud line there. It's just unbelievable. One of the grad students on our project took this photo. This is not a stock image. It's from a member of our group. Here's what our real experiment looked like on the mountaintop. We had three main sites, three main parts to the experiment. The transmitter station, which I'll talk about in a moment, that's where we've created and emitted our pairs of particles. And then the two detector stations. This is again a real photo that Jason took on his in panorama mode on his iPhone. In fact, that's Jason's shadow. So that's, you can see it wasn't a professional photo. So let's talk about the transmitter station first. What's going on there, again, in cartoon form, is we have a laser that's emitting light of a very particular frequency. In fact, it's very close to this shade of purple. You can see it with our, it's visible to human eyes. It's within the visible portion of the spectrum of really quite beautiful purple. We're shining that laser into what's called a nonlinear crystal. This has a very particular and helpful property. When light of a very specific frequency, this purple color, is absorbed by the crystal, it enters the crystal will absorb that light, that photon, and emit pairs of photons such that the total energy momentum balances. So these are of a lower frequency than the incoming one, because you have two of them that have to add up to the total energy or the total frequency coming in. So this is called the pump laser. Tune the frequency really right so that this nonlinear crystal will absorb single photons coming in from the laser, emit pairs, okay? So here's what it looks like. This is actually a shipping container that Anton shipped over from his group in Vienna with the laser and the optics in it. So here's the optics table. That is, it's hard to see from this angle, that's the laser and the crystal. And then they're piped by optical fiber, and they're literally broadcast out these windows across the island. So we're gonna send photons through free space across the island in that shipping crate makeshift laboratory. It turns out if you're not very careful, and there's an unusually strong gust of wind on a mountaintop, then you might lose your whole experiment down the side of an 8,000-foot cliff. We came close. The two grad students who had been sitting in our lab, luckily, are very, very smart and self-preserving. So they started hearing the wind and feeling the thing shake and got out. So one of them was able to get, from a point of safety, take this photograph as we almost lost that whole thing down the mountain. So it turns out if you rotate your optics table by 90 degrees around a poorly chosen axis, you're in really big trouble. So we smashed this stuff inadvertently. Here's the shattered windows. Here's our laser and our super fancy crystal on the floor. Not good news. This was 3 weeks before our observing window during calibration measurements. So then the nice folks on the Roque de las Muchachas Observatory were able to put our lab back and secure it with an enormous cement block, which of course we should have done the first time. We were able to get a replacement crystal. The laser turned out was not terribly damaged, so we're back in business. I just want to tell you what are real experiments like. You know, we talk about conspiracy theories. We think that's like a hidden variable conspiracy right there. We were clearly getting close and like, nuh-uh, we're going to disrupt your experiment. So that's how I choose to interpret that bit of bad luck. Anyway, so that's what's going on in the transmitter station. Pump laser, nonlinear crystal, we're making the particles Alice and Bob in this optically active crystal like that. And then we're transmitting through the open air across the island about ½ a kilometer in each direction. You can see the alignment optics here. So this is now a photograph taken from this receiving station looking back toward the source. Obviously, you have to do this at night. So so you get some very stunning photographs. This is not the actual entangled photon. This is a laser to help make sure that all the electronics and detectors are lined up. This is the alignment optics. But you can see, you know, it's really human distances, ½ a kilometer to make sure things are lined up really quite precisely. And then in terms of the analogy, at these distant receiving stations, that's where we're going to then pose these questions to the entangled particles. That's where our pretend waiters will measure dessert choices. Actually, they're photons, and we're going to measure polarization along different orientations. So first, let's talk about that space-time arrangement. Remember, the first loophole about locality asks whether any information could have gotten from this side to that side to account for the strong correlations. And the short answer is no. That the travel time for the light, the time it takes for the light to be created, travel all that way, and actually complete a measurement is about 2 microseconds. And the light travel time to send a single signal from this side to that side is more than 3 microseconds. We close the locality loophole. However, because we're sending these photons just through the open air, we're actually missing a bunch. We are not collecting enough to close that second loophole, that so-called fair sampling one. So we're closing locality. By design, we knew we couldn't close the fair sampling loophole with this design. But our main goal was to close or address that third loophole. And that's where these amazing, really quite astounding instruments come in. These are each 4-meter telescopes. They have polished mirrors about 13 feet across, some of the largest optical telescopes on the planet. And we got to use 2 of them at the same time. These are in high demand. what we're doing is with each of those telescopes, performing real-time measurements of different, very distant quasars. So this one on one side is looking at that direction of the sky. The telescope a kilometer away is looking in the opposite direction to a different quasar, other side of the sky. Performing measurements of the color of that quasar light, the frequency, every millionth of a second, every microsecond. If you perform measurements of the frequency of any astronomical object on that time scale, you get basically random noise. Sometimes it looks more blue than average. Sometimes it looks more red than average. Blue, red, blue, blue, red, whatever. So with very fancy, very rapid electronics, every time we measured a bluer than average cosmic photon at one telescope, that would arrange the associated detector to perform one kind of measurement on the earthbound entangled photon, which had not yet arrived. So we emit the photons, they leave the source, then we determine what question to ask by a very quick measurement of a cosmic photon. Then we rotate the polarizer all in a space of about a microsecond. If the light happened to be more red, then by the time the entangled photon arrived, we'd perform the complementary measurement. Okay, we do that 20,000 times, 20,000 pairs of photons across about a kilometer of distance. And we found very clear violations of Bell's inequality, in fact, by 7 and 9 standard deviations, respectively. Some very, very high evidence, very clear violations of the inequality, with the decisions about which measurement to perform dating back 8 billion and 12 billion years ago in cosmic history, even though the actual characteristic of that light we measured that microsecond did not yet have time to reach the pump laser or the distance detector. So the light had been traveling for 8 billion years, the more recent one, 7.8 billion years, and yet had not yet gotten to anywhere except its closer telescope. So there's no way for the source of entangled particles or the distance detector to have a preview of the characteristic of that astronomical light. So we pushed that third conspiracy back roughly 8 billion years. Now let me wrap up. To account for experiments like even these latest ones, one could either say, I'm sorry, Einstein, we really, really gave it a good try. Local realism does not describe our world. Or, if you really want to be an Einsteinian, you could seek to retain Einstein's really cherished pair of principles, but now you have to do some pretty convoluted mental gymnastics. To account for our group's experimental results, you have to appeal to that second loophole, fair sampling, but then appeal to loophole 3 for the other experiments. So how did nature know to exploit one versus the other? Or you assume that nature really does exploit this third conspiracy, this coordination in the past, and then just engineer them appropriately early ago, 8 billion years ago. In fact, we pushed back that moving wall by 23 orders of magnitude compared to prior experiments. Or you say it actually is literally the beginning of time. It's all initial conditions, and my decision about what measurement to perform, and the NSF's decision about whether or not to fund my grant on my third try, but not my second, and the decision of the rain clouds to rain out our first 2 observing nights, right? That these things are somehow all determined at the Big Bang. That's conceptually self-consistent, though not very satisfying. Or I have colleagues who say, no, it's actually things can move from future to past. Maybe it's a retrocausal explanation that's at least consistent with Einstein's equations, even though, again, it's hard to square with other elements of experience. That's what's left, as opposed to anything in between. So I hope I've convinced you that these cosmic Bell experiments leverage the very, very cosmic scales of our universe as a whole to test the foundations of quantum theory. They very tightly constrain Einstein-like alternatives to quantum theory in a way that we've never been able to do before, and as is probably clear, are a lot of fun to work on. So just like last time, I want to share some of my own favorite reading suggestions that I hope will be helpful for you and your students. These are all very accessible books. I mentioned Louise's book earlier. Anton, my colleague, wrote a lovely book more about some of the experiments he'd been working on up through 2010. The book's been out a while, but how do you use these lasers and these fancy detectors? I wrote a book about some of the unconventional characters who cared about this stuff in the 70s and how they tried to put this to work. Some much more recent popular books, and again, my own. Or again, for you, or indeed for your maybe more ambitious students, I again encourage you to check out the MIT OpenCourseWare site. So I'll pause there. Again, I'm sorry for running a bit long, but I'd be delighted to stay longer, and I'm happy to chat if people have questions. Jared, please go ahead.
Hi, David. That really is amazing experiment. After reading the book, I wasn't exactly sure how it all worked together, but now seeing that. It really is great. My question is, so I'm getting down the quantum wormhole,
Yep.
and the question is, so you talked about in the last class neutrinos. Here you're talking about photons of light,
Right.
they're vibrating. I originally learned quantum mechanics talking about electron spin.
Mhm.
Where does the breakdown happen when you start to get to bigger particles?
Yes.
Or what other small scale particles have been studied? And this was my question to you, is the unified theory, because my kids ask, all right, so what are we doing now? And I always tell them, well, there's the quantum mechanics and special theory of relativity, and we're trying to put it together. So where does the breakdown happen, and what else maybe small scale have we looked at that we don't know about yet that might be purposeful in experimental data collection later on?
Thank you, Joe. No, that's a great and very juicy question. It's definitely on my mind, on many of my colleagues' minds, and students too. So you're right. So we have these two, I would say, I'll editorialize, two immensely beautiful, immensely successful theories of nature, by which I mean quantum theory and the general theory of relativity. And they've each been tested in very, sort of exotic and I think clever ways and thorough ways, and neither one has ever been found in a lie. General relativity is beautifully consistent across a mind-boggling range of length scales, from millimeter. We're literally able to test predictions of gravity of general relativity on millimeter distances to the scale of the observable universe. That's a wide range of distances, right? And likewise, quantum theory, as I mentioned, we can test these things to say trillionth parts per trillion accuracy as well. And neither one has ever so much as hiccuped yet. And yet, again, as you're rightly saying, there does not yet exist any theoretical framework in which the two can mesh and seem to be mutually consistent. So we have like this epic showdown, right? Like they're both incredibly beautiful, incredibly successful, incredibly thoroughly tested and on a strong empirical base. And we know they don't play well together. They just don't fit. And they haven't for roughly 100 years. So that continues to drive a lot of effort among physicists. There's some really clever ideas that maybe experiments, not literally the ones that I've just described, but maybe some tweaks on those, maybe could begin to probe this kind of weak joint, just exactly as you're asking, like where's the weak spot in when we try to put these together. And that's to try to test a kind of let's call it gravitational entanglement. It's only theoretical. It's never been demonstrated as far as I know, although there are efforts to do so. What if you have things like entangled particles of some substantial mass, but still clearly subject to quantum theory, so small enough that we are confident using quantum theory, and let them fall in some gravitational field and have that affect our description of them, and then subject them to some kind of very hypersensitive test. Are there basically gravitational entanglement versions of Bell's inequality that could be even formulated on paper, let alone tested experimentally? And I have colleagues who think about that sort of head on. In our experiment, what we did was take the gravity side totally for granted. We said, we're just going to assume for the sake of argument for this experiment that gravity behaves uniquely as Einstein described it, and that the universe has been expanding exactly as modern cosmology describes it in the framework of kind of pure general relativity. We've had to take that sort of on board and hold that constant while we test quantum theory. And so in a sense, the question is, could we try to imagine an inverse experiment, use the strength of quantum theory in some sense to test some exotic or unexpected gravitational situation? So again, I don't work on that directly, though I find it very interesting. And there are these days people trying to get closer to real experiments in that direction, whereas before it used to be just kind of pie in the sky. Another question that comes up more theoretically is, I mean, actually come back maybe to the question that who had asked earlier? I can't remember. Maybe it was Barry or Joseph. Maybe we can account for quantum entanglement if we get a little more creative on the space-time side. We keep assuming that space-time is some kind of continuous, kind of fabric, smooth fabric with no features to it, no topology to it. What if there are wormholes, sort of self-consistent punctures, like shortcuts through space and time, where an object in principle could get from point A to point B not by traveling the way that you and I have to, taking the long road, but taking the shortcut. A shortcut would be, for example, a wormhole through space-time itself. Then it could be that everything's obeying Einstein's local rules. It's just there are paths through space-time we hadn't taken into account. That's hypothetical. I find it not very likely as an explanation, but that would on the plus side, that would get us closer to the kind of mechanical A led to B kind of narrative, visualizable narrative of the sort that I argued earlier we don't really have for quantum theory. So that's an area where other colleagues are pursuing, that maybe entanglement is sort of fundamental, and it's our picture of space-time that had been a little too oversimplified before. That's a direction. I don't know if that's going to pan out. But tell your students that it remains a wide open question, and that's why they should come help, because we need help. we need fresh new ideas. That much is uncontroversial. Barry, please.
You're muted.
Yeah, Professor Kaiser, nice seeing you with Alan Guth and Anton Jellinger. Both of them are my personal heroes, especially Alan Guth. He's very famous. I mean, he's very famous. I don't know why he doesn't win the Nobel Prize. I think both of them won Isaac Newton Prize.
Yes.
Sometime ago. Anyway.
Yes.
I have a question. Like the last time I asked you about qubit, I know Anton's work on qubit is really mind blowing. He's can you give us some understanding of how he realized the quantum teleportation of qubit?
Yes, thank you, Barry. That's a great question. So, and Anton is a very dear colleague of mine, and it's been one of the joys of my life to get to work with him, and separately also with Alan, who was my PhD advisor. I've known him for a long time. So you said they're both personal heroes of yours. They're personal heroes of mine too. So we share that, among other things. So Anton loves doing these kind of larger than life experiments. I think it's partly why he was excited when Andy, Jason, and I pitched our idea to him. So he not only was among the first to demonstrate in a real experimental setting that quantum teleportation is possible, he did it across islands in the Canary Islands, 144 kilometers apart. That's why he knew to install our experiment in the Canaries, because he's been doing experiments there for decades. So quantum teleportation might take a little while to explain. I'm not sure I'll get it all right on the fly. But the critical thing there is it involves entanglement, and it's a way to transfer a quantum state from one object to another. It takes advantage of this spooky connectedness, but we need another ingredient. And we need a classical communication channel that could be carrier pigeon or tweet, but it's not inherently quantum mechanical. Basically, to complete the transfer, you have to tell the distant party what second measurement to perform. You distribute entangled particles, you perform one measurement here, and then you have to tip off your partner with a tweet or with a phone call. Now, if you rotate your polarizer exactly this way, you'll instantly have the quantum state that I had right here, and I'll lose it. So the quantum state is somehow conserved, even though the information seems to travel instantaneously, except still with a catch, that to get the instantaneous transfer, we had to have a slower than light communication channel. So it's still not violating that no fast and light signaling. But what Anton showed is that can be done with real instruments in the real world across 144 kilometers through thin air, not even with fancy optical fibers. So again, I encourage you, I have to admit, I get confused on the quantum teleportation experiment, the protocol. I get confused, I forget the details a lot myself, and I go back to the Wikipedia entry on it, and this Wikipedia entry, at least, I will say, has been actually, to me, quite helpful. So I recommend, just if you're interested, go to the Wikipedia page on quantum teleportation. That's a perfectly good place to start, and it explains a bit more the steps involved. But the crucial things are distribute entangled particles, much like we do, and make a phone call to your friend and tell them exactly what remaining measurement to perform, and then you can do this otherwise kind of magic seeming transfer of the quantum state. And again, as I say, Anton, as you rightly point out, has been involved in the real world demos of that for a long time. He's quite amazing. Peter, please.
So I have
two quick ones. Number one, I mean, like obviously Einstein's theories and quantum mechanics have lived kind of together for all these years. So the first question is, as a physicist yourself who spends so much time on this, are you satisfied without having some type of a unified theory? Like, will you be able to say, okay, I've done my work and I'm happy with everything without getting to that answer? And number two, I'm wondering if in the theoretical physics world, if there's any talk of getting closer to those answers with knowing what happened prior to the Big Bang, if that's still like a hot place to look and stuff.
Thank you, Peter. Those are both really juicy questions. Let me take the second one first. Ironically, that one feels easier to me. It's closer to home for me. Part of what we have to do is be clear, and I don't mean you, I mean like the community. It's something we all struggle with, even in professional physicists. Be clear about what we mean by the Big Bang. And what it has come to mean for the specialists is, I think, a bit different from how it's often used more broadly. To us, to Alan Guth, to our research group, to our colleagues all around the world, we now use the term the Big Bang in a more restricted way to mean the point at which the standard Big Bang evolution of our observable universe began. And that's being agnostic. Then it's no longer itself a huge conceptual leap to say something could have happened before then. Maybe something was likely to have happened before then, right? So if we, and that's when I say the Big Bang happened 13.8 billion years ago. I mean that physical process of a kind of expansion from a very, very small volume, spatial volume, expanding at a certain rate, filled with certain kinds of stuff. So the Big Bang is a model that accounts for many kinds of physical phenomena that make specific predictions what we should see in the sky today. That process began, we can now measure with really amazing accuracy, that began 13.8 billion years ago. Even being able to say that is more than I could have said when I was in grad school because the numbers were so uncertain. So the uncertainty, the error bars on that number have come way down. But that leaves open then quite generically what set that expansion in motion. And what Alan Guth should win the Nobel Prize for, I'm going to go out on a limb just as Barry has, I totally agree, was for providing our current best explanation for, as he likes to put it, what put the bang in the Big Bang, what started what we now call the Big Bang. And that was a period of exponentially rapid stretching of space, a period called cosmic inflation, which would be before the Big Bang, because it's after that initial stretching that the standard Big Bang evolution kicks in, at least according to our best theories. And then something could have happened before inflation. In fact, many things could happen. Some people, some colleagues, pursue actually kind of infinitely cyclic models where there could have been a whole series of Big Bangs and big crunches, neither of which necessarily had to go to an actual singular point, but all would have had to have been condensed very, very densely. And then there could have been a phase of inflation and then standard Big Bang. And then maybe there was a crunch where things fell back into a very small volume again and start. So that's one possible model, a cyclic model. Or there was a finite expanse earlier than inflation began, and then something started inflation, and then the Big Bang followed. What I'm getting at is we can pose all these questions without solving quantum gravity so far, because even inflation happens when gravity is sort of self-consistently classical. In space-time, we can treat without worrying about some sort of inherent quantum fluctuations of space and time. Again, I find that amazing. We can make these predictions for all these kinds of things we should be able to measure in the sky, and our colleagues do measure these to high accuracy now, better than percent level accuracy. Patterns in the distribution of the primordial light, patterns of distributed galaxies, many, many kinds of things like that. And we make those predictions by assuming that space-time was already behaving just as Einstein said it should, classically. So now that's an era before the Big Bang where we still seem to have a self-consistent classical description of gravity. Now, what came before that? Then there be dragons, right? So then we don't know, and there's no shortage of ideas, and there's also no shortage of, there's no abundance of evidence, right? So then it's like, I like my idea, I don't like your idea, which is code for I like me and I don't like you sometimes. You know, it can get to the usual kind of human foibles very quickly. So that is an area of really active ongoing research, but it's nonetheless the case that we can describe the Big Bang itself in this more limited meaning of it, and even for the prior to the Big Bang, and make predictions from before the Big Bang and match those to the sky today. And I find that just, I hope you'll tell your students about that too. I find that's what I mostly work on in physics. I find that just exhilarating. Do I find it personally satisfying not to know how these things fit together? I'm frustrated, but I know I'm in awfully good company. I mean, if I was the only person who didn't know, then I'd be really annoyed, right? But I get to, I mean, let me turn it around and be a bit of a Pollyanna and say, you know, physics isn't done. And what an amazing adventure to try to continue with more young, smart people, right? I mean, what a great thing to try to get more sets of eyeballs on. And again, that's why I hope you'll bring some of this back. I'm sure you will, and already have been, to your students now and in the future. Because this is a big challenge. And sometimes we've cracked big challenges, right? We didn't understand the atom for a long time. Now we can make atoms dance at our whim, right? We didn't understand the Big Bang for a long time. Now we can put up satellites and measure things to better than percent, right? So we can do this. We've done many things like it. And so the fact that it's not been solved in 100 years doesn't mean it's unsolvable. It does mean we're kind of stuck. Like I think we're in a rut, at least from where I see it. And so we can either play the glass half full or glass half empty. And there's some really quite exhilarating speculative ideas. And there's some ideas that I find silly that might nonetheless be right. You know, and that's where we are. And part of what I find fun, going back to I think Jared's earlier question, is the challenge is, how might we know, even if we have a favorite pet explanation, what kinds of ways could we try to get empirical evidence down the road? Again, maybe a souped up cosmic bell experiment, or who knows what. So that's enough to keep getting me out of bed in the morning, even though I have to go to bed at night, you know, as a personal failure. Like it's, you know, it's okay. I think it's okay. Jim, please.
So,
oh.
Yeah. Oh, and I was just going to say, Thomas also has a question in the chat, and I want to make sure that we acknowledge that. And I know that we're taking a lot of your time, Dr. Kaiser. So let's make Thomas and Jim's questions the last questions.
Very good.
Oh,
Thank you, Renee.
I should say Matt had his hand up before mine.
I'm happy to take that one as well. I'm not in any rush, and I just apologize for running long for all of you. But so please don't.
No.
I won't be offended if you have to drop off, of course. So Thomas, you have an interesting question in the chat. How would I answer a student that invokes the simulation hypothesis when we reach the subject of quantum entanglement? Would it be correct to say that if our universe is simulated, it would be then it would be the spooky action? I guess one way I'd put it is to say that we could think of one version of the simulation hypothesis as akin to one of these answers that's left on those last few slides I mentioned. Maybe it all comes down to programming, to initial programming. Maybe we were programmed to think we wouldn't get telescope time, but we did. Maybe the NSF program officers were programmed to reject our grant proposal two times and then squeak it through the third, right? That would be consistent with some simulation where we think we're acting with what feels like free will, but it could be consistent with some sophisticated programming. We're all basically, you know, androids. I don't know how to disprove that. One could make a consistent story with that, although you can see how it gets strained, but I don't know how to catch that in a lie. And I think that's a species of the kinds of explanations that are left. And what I want to emphasize is we're left to that level of outlandishness after experiments like Cosmic Bell. So to account for our measurements, our experiments, either we say it's quantum mechanics, I have free will and it's quantum mechanics, that's a happy answer, right? Or what's left is I don't have free will and it was all laid down in this initial simulation, you know, by the master programmer or whatever. And almost everything in between now has been constrained or ruled out. So that's my take on the simulation hypothesis. It would have to be very careful, going back again to Barry's point, that each observer has a self-consistent set of history, so that she doesn't wake up one morning and suddenly her entanglement went away when it shouldn't have. There's no hiccup, because our experiments haven't found hiccups yet in testing entanglement when we do them carefully. So I think it would be a version of that. And I would just encourage your students to think about what would it take to try to test that hypothesis. Maybe there are ways, and again, maybe I just haven't thought of them yet. Let me go to Matt then, and then to Jim, please.
I had put my hand down because I'm not sure I've articulated my question as well as I want to. But this idea of relativity and quantum mechanics being at such odds with each other, my question is, I'm not entirely convinced they are. Okay. In the sense of, I know I asked last time about the collapse of the wave function and how does that happen, what makes it happen, all of that kind of business. And it kind of feels like because this quantum entanglement can't be used to actually transmit any information, it feels like it's not really violating relativity in that sense. That you can't actually send any information. It all has to do with the collapse of this wave function in these two different places simultaneously, and we don't really understand that. Is that correct? Is that the only way that like grinding of gears between the two theories happens?
So, thank you, Matt. Yes and no. Meaning, yes, I totally agree with you that there is no immediate contradiction between quantum entanglement and relativity, exactly for the reason you said, which is why I wanted to emphasize that, because people thought it might. I mean, that's actually when I wrote this earlier book called How the Hippies Say Physics. These folks thought they'd found a way to break one or the other, that entanglement would break one or the other, and they thought entanglement would break relativity, and it doesn't. And it was their pushing that clarified exactly why they just barely sneak through in this clever way. So I agree that entanglement on its own does not somehow violate relativity or vice versa. So that's right. But there are other concerns, other reasons why the two larger sets of ideas still don't mesh. And by that, I mean, every other force of nature, electromagnetism, the strong nuclear force, the weak nuclear force, the way we can describe all the, frankly, forms of matter of which we're made and that fill the universe, can all be formulated in a quantum mechanical framework from the beginning, based on things like probabilities, superpositions, entanglement, uncertainty principle, the things that some of which we talk about in these sessions. And there's no self-consistent pencil and paper description of gravity that's consistent with probability, superposition, entanglement, uncertainty. They're ideas, they're partial, but those are what break. Or vice versa, there's no way to describe quantum systems that includes all the features of relativity, not just no signaling, but also that it has definite properties each moment, right? So we have superpositions that can't be used to send messages faster than light, okay, but superpositions aren't how we describe gravity. Right? Even that alone is different. So it's those other conceptual gears that don't mesh, or just more formally at the mathematics. So for example, it often shows up where if we try to write down a kind of uncertainty principle for space and time, much as we might for position momentum of a given particle, what if the fabric of space and time itself is subject to unavoidable quantum jitter at an appropriately small distance scale, so we don't feel it when we walk around day to day? Then it turns out, formally, mathematically, those models blow up to infinity. They don't yield predictions. We can't form finite mathematical statements about A should cause B. We can pose well-posed questions and get the answer infinity, which is not a well-posed answer, right? So it's those and that is a mathematical symptom of the conceptual disease that we describe space-time not subject to uncertainty, superposition, and probabilities. And we describe things like quantum particles, in the different language. So that's, I think, where the larger sticking points or series of sticking points tend to come up, if that helps. Great. Jim, please.
Yeah, thank you. I just wanted to circle back to the one of the last things on one of your slides was talking about like what are some of the ways that we could like what are other loopholes that we haven't addressed yet? And I didn't know it was attributed to Tuft, the idea of superdeterminism, that like the light from the quasars you measured, they had talked to each other billions of years before when they were close together in inflation, and like the whole universe is in on this game, and that the correlations were built into it from the start, into the universal wave function. How would we ever address that?
That's, Jim, thank you. And to be cheeky, because it's late, I would say that's Nobel laureate Gerard 't Hooft's problem. Like, come on, what have you done for me lately? He's a remarkable colleague, but I mean, but I agree with you. That's why I don't adopt that as my favorite answer. My favorite answer is it's quantum mechanics. Come on, and I can't describe that in a picture, but it's quantum mechanics. And I more charitably to Hooft's to his credit, and indeed it's not only him, but he's, I think, the most prominent physicist who's been articulating this. He's saying that it's at least self-consistent to build theoretical models of that form. It's not ruled out by any of these tests. And then the rejoinder, I think, is just to say, well, what test ever could rule that out? And that's when many of us start saying, much like the simulation. That's the version I thought was akin to the simulation hypothesis to Thomas. That's what I think of as really kind of conceptually quite, maybe even the same, or versions of the same thing. And that means I don't know how to make them amenable to further empirical or experimental test. Because even my effort to test them would have been foreordained, let alone the thing that came out of my detector, right? That's the way that argument goes. So it's certainly, I should say, it is right in drawing our attention to the fact that we think we can operate, we think we can make free choices with equipment that's been sharing a past light cone for most of the history of the universe. Let's be careful about causality. I mean, I actually really admire that part of it. And that was, we share that in our impetus in thinking about cosmic bell. Just because you turned on a random number generator from a black box on your desk, you know, what could have gotten that black box yesterday or 12 billion years ago? So in that sense, they share, I think, some of the same. We go down part of the road together part of the way, and then we part ways. And drawing attention to the shared causal past of the elements of our experiments, that seems to be really important. And then the question is, do you push that to the level, to the ultimate level, and then say, I can't subject that to further test? Or do we say, okay, subject to these assumptions, we've constrained alternate explanations to a box from when the universe was 8 billion years was 8 billion years older ago, meaning 6 billion years old roughly. And that's the fork of the road that we've chosen to take. But I do put his name down to say really smart, accomplished people, I mean, Nobel laureates in his case, do take that other explanations quite seriously. And I think there's reason enough to at least give it some thought, even though I happen not to vote with that with my pencil.
Wow. I feel sure that this conversation should just continue and continue. And if we just had dinner delivered to us all here, we could just keep talking. But this has really been absolutely fantastic. And so I want to thank you so much, Dr. Kaiser, for being with us these 2 sessions, and for all of you teachers for having such great questions and being as rapt as I have been during this set of presentations.